Welcome to this explainer. When we're writing object-oriented code, our classes almost never just live in total isolation, right? They've got to talk to each other, rely on each other, and sometimes even completely own each other. So today, we're going to bridge that gap between how these relationships actually function under the hood in your C++ code and how we map them out visually on a UML canvas. Get ready, because we are going to literally translate abstract logic into crystal clear visual diagrams. So, here's our roadmap for the explainer. We're going to kick things off with a class relationship overview, then examine dependency and association, followed by aggregation and composition. After that, we'll dive right into UML diagram basics and visualizing those UML relationships, and finally, we'll wrap the whole thing up with a solid exam review and recap.
Okay, let's dive into this. Section 1, Class Relations Overview, our hierarchy of links.
So there are really 5 core ways classes interact in object-oriented programming, and they form a very clear, distinct hierarchy. We basically climb a ladder here. We start way at the bottom with dependency, which is just a super simple user relationship. Then we move up through association, aggregation, and composition. Those represent different, strengthening flavors of has-a and whole-part connections. And finally, we hit the absolute strongest bond at the top, which is inheritance, a strict is-a relationship. So remember, this list climbs sequentially from the absolute weakest relationship all the way up to the strongest.
All right, starting at the bottom of the ladder, Section 2, Dependency and Association, the user connections.
First up is dependency. And this is a very, very weak temporary relationship. It basically happens when an object of one class just uses an object of another class for a short amount of time, usually just passing it right into a function to perform a specific task. What is absolutely vital to understand here is that their lifetimes are completely independent. Like the creation or destruction of one object has literally nothing to do with the other. Plus, it's unidirectional. The class being used is entirely unaware that the dependent class even exists. Let's actually see this concept in action with some real C++ code. And hey, here is a classic, highly exam-relevant instructor's hint for you. Just think of your OStream and iStream objects when you're doing operator overloading. This specific line of code perfectly illustrates dependency. The point class uses the iStream object to extract data, but, and this is key, the stream object isn't actually created inside the point class. Their lifetimes are totally independent. Honestly, the input stream class doesn't even know the point class exists.
Moving slightly up that ladder, we've got association. Now, this is still a user relationship, so it remains a weak connection with absolutely no ownership of the objects involved. You have independent objects interacting to perform tasks, but they strictly maintain their separate lifespans. The main difference here from a standard dependency is that association can actually be bidirectional. The objects might know about each other, and you'll see these associations map out in one-to-one, one-to-many, or even many-to-many configurations. Now that we understand use-a, let's look at has-a. Section 3, Aggregation and Composition.
Okay, let's break down how we actually implement aggregation in C++. Aggregation basically means one class is a collection of another, but they still have entirely independent lifetimes. So to code this correctly, you absolutely must use a pointer to the aggregate class object. Look closely at the logic here. The whole class does not create the part object itself. And because of this, when the whole object is destroyed, its destructor does not destroy the part. Inside that destructor, you literally just set the pointer to null pointer. So here is a massive exam tip. Pointers maintain those independent lifetimes. Don't forget that.
Now this brings us to a huge edge case where students constantly get tripped up. They confuse aggregation with its stronger cousin, composition. Think of it like this. Aggregation portrays a logical part. This means it's relatively simple for the part to be removed from the whole, or a single part can even be associated with multiple wholes at once, kind of like a teacher who works in multiple departments, right? Composition, on the other hand, is a strict whole-part relationship. In composition, the lifespans are totally shared. If you destroy the whole, the part is inherently destroyed right along with it. No exceptions.
All right, let's shift our narrative from code to canvas. Section 4, UML Diagram Basics, Communicating Visually.
The standard notation for a UML class is really just structured as a simple rectangle, and it's divided into 3 specific sections, and this brilliantly illustrates the class structure. The top box contains the class name, which, by the way, is italicized if the class happens to be abstract. The middle box houses the attributes, or fields. And finally, the bottom box outlines the operations, which are basically the actions or functions unique to that specific class.
Now, when you're actually writing out those operations in that bottom box, there's a very specific literal syntax sequence you need to follow so you can perfectly replicate it on your assignments. Step 1, define the visibility. Step 2, write the name of the method. Step 3, list the parameters inside parentheses, strictly formatted as name:type. And finally, step 4, define the return type, separated by a colon at the very end. Oh, and quick side note, make sure you omit the return type for constructors.
Let's draw some lines between these boxes. Section 5, Visualizing UML Relations and System Architectures. You know, sometimes connecting two classes spawns a brand new concept entirely. When we map this out, we see what are called intersection classes. Just look at how a grade is actually just an intersection of a student and a course. A grade only exists right where those two ideas meet. Similarly, a job can be viewed as the intersection between a person and a company. It's just a great way to capture this shared reality visually.
Then, for our absolute strongest relationship, inheritance, or that is-a relationship we talked about, UML uses a generalization hierarchy. We'll use this vehicle taxonomy as a visual anchor here. Now, you read this from the bottom up. Notice how the lines with those hollow triangle arrows point up to the more general base class? So a truck is a land vehicle, which in turn is a vehicle. It just clearly and cleanly maps out all those inherited traits.
So the crucial point is how we distinguish our has-a relationships visually. We need to look closely at the diamonds connecting the classes. When you see a hollow diamond connecting a desk to an office, that is aggregation, that logical part where, a desk can easily exist without the office. But if you see a solid, filled-in diamond connecting a room to a building, that is composition. It's a strict whole-part bond. Literally, if the building is demolished, the room ceases to exist. So remember, hollow means independent aggregation, solid means strict composition.
Okay, time for the ultimate cheat sheet you'll want to pause and memorize. Section 6, Exam Review and Recap.
Let's do a rapid-fire summary translating everything from UML right back to the C++ code you know. For visibility, a plus symbol is public, a minus is private, and a hashtag is protected. Simple. For relationships, dependency is just short-term use, like our stream operators. Aggregation in code means using pointers to keep those lifetimes independent. Composition, that's a strict whole-part bond where lifespans are totally shared. And visually on the canvas, remember the diamonds. UML aggregation gets a hollow diamond, and UML composition gets a solid diamond. I'm going to leave you with a bit of a provocative thought to really test your mastery here. If you delete a university object in your C++ code, should all of its associated departments be inherently destroyed as well? Think about the real-world logical reality versus strict code ownership. And more importantly, if you drew this exact relationship out right now, would you use a hollow diamond or a solid diamond? Does your visual UML diagram perfectly match your underlying C++ logic? I'll let you mull that over. Thank you so much for joining me on this explainer. Keep practicing those diagrams and happy coding.